So hi everyone, my name is Klaus, and today I would like to present some joint work with some of my colleagues, from Sebastian Brandt, Laurent van Bever and Roger Wattenhofer. And this talk will be a bit in the line of the talk that you saw from Stefan earlier, though this time not about loop freedom and waypoint enforcement, but more in the area of bandwidth requirements. So let's say that you have a small sample network and you have some flows in this network, and all the flows have size 1, all the links have size 1. And now you're in a situation that maybe this green source would like to send as well to its destination. And then if you would just put in this green flow, then you would have congestion on this link down there. However, as you can see, you could organize your network better, maybe in an SDN with some centralized controller that tells the nodes what to do. So you could just change your network to this behavior, and then all the flows would fit in without any congestion. So let's actually do that. Let's let the controller send out messages. Dear sources, please change your behavior to the dashed flows. And then if they would all change at the same time, everything would be great. But as pointed out in the talk by Stefan earlier, there are some problems. Some nodes can react with some delay. And then if all the other nodes already implement their new behavior, for some time we will have congestion on this link. And in practice, this can range sometimes that maybe some switches straggle up to 100 times longer than the implementation time of the other nodes. And then if you have congestion for, let's say, 20 seconds, that might not be so good. However, in this case, we can easily fix it. As you might have already seen, what we can do, we can just order these updates. So we can just put the red flow up first, then we put the blue flow up, and then the green flow. And then you have migrated without congestion, but of course at the price of some longer migration time. And this concept of some consistent migration of flows without congestion was introduced some years ago in a paper called Swan. And there the idea was that the flows can either be on the old route or they can be on the new route. But no matter where they are, if you add up all the flows on the links, you should not violate any capacity constraints. And sometimes ordering is not good enough. Sometimes you also need to split the flows. So if you take a look at this example where you have a blue flow going down and up, and then the green one is just the other way around, and the flows have a size of 2/3 and the links have a size of 1, then if you would switch either of them or both at the same time, you would violate this consistency constraint. So what you need to do is you need to look at the free capacity. And in this case, you have a free capacity of 1/3. So you can just move 1/3 of the flow over, like this. So you split the flow into 2. And then you do it again, and you have migrated without any congestion. However, this approach sort of no longer works if you don't have free capacity on the edges. I mean, what you could do, as for example discussed in Swan, you could turn down some background traffic, then migrate, turn the background traffic back on. However, in this talk, we are going to look at if this is not possible, so a bit more from the theoretic side. So in this case, we cannot migrate without congestion. However, what happens if you have some alternative routes, like one down here? Then we can think of this a bit as variable swapping. We put just one flow down there, then we put the other one up, then we put the other one back, and we've migrated without congestion. And one current approach is sort of like to look at in how many steps can we do this. And you can put it into an LP. Can I do this with 1 intermediate steps, with 2 intermediate steps, with 4 intermediate steps, and so on, until you found a solution. However, from a theoretical point of view, this approach has one problem, maybe not so much from a practical point of view, because in theory, the number of updates you might need can be unbounded. So for example, in this case, if you just have like this extra capacity of epsilon, you might take 1/epsilon updates to migrate without congestion. So can we still solve this problem in a polynomial time? And by solving, I mean, can we decide if there is an update process that migrates without congestion? Because if yes, then we would already have some upper bound and could also put it into an LP for an optimal solution. And if no, then we might think of some other solution, like in the Dionysos paper, for example, to rate limit some flows to get on without too much congestion. And the answer is yes, we can decide in polynomial time, and we will use this idea of free capacity. So if we have free capacity on all the links that we need to, then we can just do it step by step. And if we don't, then let's try to create this free capacity. And we are not going to use some LP approach, but we are going back to a combinatorial approach to decide in polynomial time. And what we are going to do is we are going to look for augmenting paths to free up link capacities. So let's take this example where we have a flow with two paths, one up there, one down. They have a size of 1 each, and the links have a size of 1 as well. And we would like to create free capacity on this link down here. So what we are going to do now, first we're going to look at where can we put extra flow, namely on these edges because they have free capacity. And on the other hand, where can we reduce the rate of flow by rerouting the flow. And this is on all the edges where we have some flow. So now if we combine this, we get the residual network. And now we can look for a path from U to V, like this. And then we can use this path to create free capacity on this link. And this leads to the following high-level idea of an algorithm, that if we don't have free capacity on the links where we would like to have free capacity, then we try to find augmenting paths over and over and over again until we are at a state where we have free capacity, or where we try to find augmenting paths for all the links that are at full capacity. And if we reach a place where we have free capacity, then we can migrate, again doing the step-by-step approach. And if we cannot create free capacity on some link, then we can show that by contradiction, you cannot migrate in a consistent way. And essentially the idea is if you could migrate in a consistent way, then you could also create some free capacity with such an augmenting path. Meaning that in total we still have a polynomial runtime, but of course we don't have any guarantee on the number of updates needed. Okay. Okay, sorry. So the question is, are we done now? Is this consistent migration also lossless migration? And as it turned out, the answer is nearly yes, because one thing that we are still missing are the packets in flight. And I would like to show this in a small example. So let's take this network down here, where you have some flow that goes along a path with 11 milliseconds shown in the solid line. And you have some new path down there, which just has a ping of 1 millisecond. And naturally, you would like to change from the slow path to this fast path. So let's say that at time around 15 seconds, you give this node U down there the command change the path. And you won't run into any clock synchronization problems or anything because you just need to implement this one command. Now we have a latency difference of some milliseconds. So what one might think is that if we change the routing behavior, we go from the high latency to the low latency, maybe with some jitter for some milliseconds. However, what we actually measured in practice is that the following can happen. Is that these packets that are in flight still down here, they go along for some time, and they join up with the packets along the new path down here. And then for a time equivalent to the latency difference, you have an incoming flow of 2, but you can only drain this flow of 2 at the rate of 1. And in theory, if the flow would actually continue to arrive with a size of 1, then this buffer would never be drained, meaning that all the extra latencies stays in the buffer. And when we measured it in a real network, we saw that, well, after some time, for example, here with UDP, the buffers were drained. When we put the data that was coming out of S to be a bit more aggressive, such that we had buffer buildup anyway, then we could also leave this running for days, and the buffer would never be emptied. For TCP, it was a bit different because there we might have packets out of order, meaning that the TCP streams would reduce the rate anyway, so we would have a smaller time until we would get the new latency. So how could you prevent this? Well, one idea would be that you just set the buffer sizes to 0, and then you would immediately reach the new latency. However, then you would drop all the packets basically equivalent to the latency difference. And yeah, that's not so good. We don't want that. However, what you can show there, if I give you a quick overlook, is that while we can decide in polynomial time that if you can, that you can migrate, that you can decide in polynomial time if you can migrate or not. If you want to look at this lossless migration, then if you know the delays in the network, that already for a single flow that is splittable, it's already NP hard to decide if you can migrate or not. However, if you put the problem a bit around in the sense that you no longer fix the latencies, but that you say, okay, we don't know how the network will actually behave. Maybe some latencies will go up, maybe some latencies will go down. And you want to then check if you can migrate in a lossless way in this model, then you can again use similar methods as before and decide in polynomial time, can I migrate lossless or not? However, this all breaks a bit down if you have unsplittable or integer flows, because then it all turns out to be NP hard again. So, yeah. So if you have, so we know for many cases we can decide in polynomial time if we can migrate, yes or not. However, that's maybe still not good enough, because if I tell you, yes, you can migrate, it just takes 1,000,000 years, that's not so good. You might not want to do that. So we thought, how can we change the problem in a way that you also have fast updates? And there the idea was as follows, that we thought, okay, these new paths where the flow should migrate to, they come from somewhere, but why shouldn't we decide ourselves as well where we put these paths? So if we change the problem from the setting that we don't migrate to some new paths, but that we just say, okay, the new flows should fit into the network and we don't care where they fit into the network, then we can actually do it for many cases in polynomial time. And to give you a small example, like when you look at this example that was shown earlier in the talk, where you need an unbounded number of updates, if you just fix the new demands, then you don't need to change anything because the flows are already in there, so why would you change them? And we can show that if we just have one source or one destination in the network, but still many sources or many destinations of the other way around, then if you have multi-commodity flows, you can always migrate in a polynomial number of updates without loss. However, where we still have ongoing work is that if you have multiple destinations and multiple sources at the same time, then how can you migrate in a fast way without generating any loss? And with that, I would like to conclude, and thank you. There's one? Yeah.
Yes, when you're splitting a flow, is there a threshold where the splitting causes reordering and, for example, you're using TCP and it lowers the throughput, and it would be better just to migrate to and generate a bottleneck because the throughput would be higher.
You mean because this splitting, because there would be like basically some loss or congestion because I split too much?
Yeah, for example, when you split, you send the same flow through two paths.
Yeah.
And that can be reordered.
Yeah, that's true.
So, is there some case where this reordering is worse than sending flows to a bottleneck link? Is there some?
Yeah, I would guess it depends on the application. If you have some, let's say you have some data transfer or so, then maybe you could say the latency differences are maybe not so high, so you just say if I have some reordering, then I can resolve it at the destination. But I would guess if you maybe do something like a Skype call or so, it might not be a good idea to split them up. But then for a Skype call, then maybe it's not so much at what this technique is targeted at, because if you have just some very small flows, then maybe you could just say, okay, we don't really change them, we just change the elephant flows. Yeah.
I didn't fully understand that the link or path that you added at the bottom. Yeah, there. Is this an artificial construct that's part of the algorithm, or is, I didn't?
Yeah.
Are you assuming there is some spare capacity there outside?
Yeah, so the assumption would be that if you don't have this path down there, then, and you would like to flip these flows, that then you cannot do it in a consistent way without rate limited then or adding congestion. And the idea was here with this extra path is that you could also explore basically like the surrounding network outside the old and the new flow paths to see if you could temporarily put the flow somewhere else and then put it back.
I have a very nice question. Can you go back to the graph where you were showing UDP and the TCP?
Yeah.
On the left-hand side, why is it that the delay is still around 11 seconds for so long? Because now you have to have traffic from that, time zero is when you implemented the split, right? Traffic should start arriving at the same rate on the link between V and T from the two paths.
So what we did was, at the source we put some iPerf running at 1 gigabit through the network. And then what happened was that basically like the packets that were in flight here, they were still arriving for some milliseconds while the flow down here was already arriving. And then, well, they got all put into the buffer. And if the sending rate would not be exactly at the link capacity, then it should be drained very quickly. But basically now we had these packets in the buffer, but the packets that were coming in at the same rate as we could drain the buffer, meaning that for some seconds the buffer stayed basically the same until maybe the sender had some irregularity and couldn't send with exactly 1 gigabit. And then at that point there was a short time window where the incoming flow was not exactly 1 gigabit. And then the buffer could be drained that way.
We can talk all this later, but it's not a small time, it's about 5 seconds, right? And then the other thing is that I would have thought that naively maybe, that it would go down to about half, because in some sense the stuff is coming at the bottom at the same rate as stuff is coming from the top, right? And the packet at the bottom will have RTT of 1. The one that coming from the top will have 10, right? So if they're roughly equally coming in, then if you do the value should go about half.
Yeah, but in this case, basically all the packets that were here in flight, they got put into the buffer, meaning even that this latency down here was no longer 1 millisecond because they all had to go through the buffer again. And then basically this path down here was no longer 1 millisecond, but 1 millisecond plus the buffer size in there. But maybe we can talk offline. Yeah. Okay, thank you.